Radio, g'day students, welcome to our lesson on the solubility of organic compounds. So the point of today's lesson is that you should be able to recognise that organic compounds display characteristic physical properties, including melting point, boiling point. Not worrying about that, just solubility in water and organic solvents, and it can be explained by in terms of those three intermolecular forces we've been talking about. So first of all, dispersion forces, dipole, and hydrogen bonds. Now they're influenced by the nature of the functional groups. And then we can also talk about the solubility of in water of alcohols, aldehydes, ketones, carboxylic acids, and halides or haloalkanes. So just remember, water is held together by polar bonds, hydrogen bonds. And so water is a polar solvent. The solute is a substance that gets dissolved. The solvent is what is doing the solvation. So that's in which the solute dissolves. Now, dissolution or solvation is the process that occurs when an ionic solution dissolves in solute and the solvent molecules surround the positive and negative ions. Now, this is a little bit different because we've been talking about organic compounds, haven't we? So we need to think about then those like solvents dissolving like solutes. So just remember that polar solvent, polar solute, and non-polar solvent and solute are the general rule to remember. But we're going to go one step further today. We're going to say, well, generally speaking, those with hydrogen bonds will dissolve it with hydrogen bonds. Those with dispersion forces will dissolve in those with dispersion forces, and those with dipole will dissolve in similar sorts of solvents. So most organic compounds are immiscible in water. So for a substance to be soluble, the solute-solvent interactions must be greater than the solvent-solvent interactions. So when the solute dissolves, the intermolecular forces of the solute and the solvent are broken. So hydrocarbons held together by dispersion forces do not have enough energy to compensate for the larger amount of energy in water held together by hydrogen bonds. So if I think about organic solvents, something like pentane and octane, they're going to readily mix because they have those similar intermolecular forces together, holding themselves together, and they are, of course, dispersion forces. And so pentane and octane will readily mix because they both held together by dispersion forces. When we consider the solubility of haloalkanes or halides, aldehydes and ketones, they're generally not soluble in water except for the smaller ones. So haloalkanes, aldehydes and ketones are held together by dipole-dipole interactions. So as the length of the carbon chain increases, the influence of the polar functional group decreases. So if I've got chloromethane, for example, what's that? That's got to have a hydrogen, and then we've got a chlorine there. That's going to be what your partial negative, your partial positive. That is going to be a slightly polar molecule. It's going to be held together, each of these chloromethane molecules held together by the dipole-dipole interactions. But there's certainly, the more carbons you get in there, the less the effect of the functional group. And so it makes it less and less polar. Now the hydrocarbon tail, or the carbon backbone, is non-polar. So as the organic solvents such as hexane, benzene and toluene are going to be able to form dispersion forces with these molecules and dissolve the larger aldehydes and ketones. Now branch compounds of ketones and aldehydes have weaker dispersion forces. So remember, they're more clumped, they're less surface area, and they're going to be a little bit more soluble in water than the straight chain compound. You can see here we've got a small aldehyde, and so it looks like a methanol or something, but we've got a little carbonyl group there, and it's forming a hydrogen bond with the water molecule there. So a small aldehyde and ketones are soluble in water, but you can see methanol and ethanol are quite soluble. Propanol is soluble, but solubility certainly decreases when we get to 4 and 5 carbons in the carbon backbone. Now have a look at alcohols and carboxylic acid. So we know that we've got the hydroxyl groups, for example, and there's going to be these hydrogen bonds. So small alcohols and carboxylic acids dissolve well in water because of the hydrogen bonds formed between the polar functional groups and the adjacent water molecules. And you can see here we've got it for the alcohol. And let's have a look at the carboxylic acid. So carboxylic acids are more soluble than alcohols because the hydrogen bonding occurs between the water molecules and the carbonyl group as well as the hydroxyl group. So here's our carbonyl group, and here's the hydroxyl, and here's the hydrogen bond. Here's the hydroxyl group, and here's the hydrogen bonding. And you can see that we've got a couple of hydrogen bonds forming for each carboxylic acid. So carboxylic acids are a lot more soluble in water. So likewise, though, in water, solubility decreases as the length of the carbon chain increases. But solubility should increase as the branching increases. And in organic solvents, the solubility increases as the length of the carbon chain increases. So let's have a look at our tables. First of all, what do we got here? Solubility increasing as the solubility decreasing as the molecular mass decreases. Solubility is decreasing, yes, as the molecular mass is increasing for alcohols. Now for carboxylic acid in the table below, you can see, well, we can certainly dissolve as much meth, eth, prop and butanoic acid as we want in water, pretty well unlimited there. But as it hits pentanoic acid, it starts to show some decrease in solubility in water. Finally, we can see that as branching increases, so here's an isomer of butanol, and you can see that it's highly soluble compared to butane-1-ol. Okay, are you able to recognise the organic compounds displayed this physical property of solubility in water and in different organic solvents in terms of those three intermolecular forces, and also in terms of the alcohols, aldehydes, ketones and carboxylic acids and halides. When you're done there, I'd like you to work on the mastery exercises, please.